In my last video, I did an integral from MIT's 2020 qualifying exam for their Integration B, and I want to look at another integral from that set, because these integrals are just fantastic. They really force you to not think so linearly about how we approach these integrals, and make a lot of lateral moves that would not seem obvious unless you had a firm grasp on what it really meant for you to be integrating this function. And specifically right now, I want to focus on this integral right here. So before you listen to me talk too much about this integral, I'd encourage you to try it out on your own. Just grab a pencil and some paper and play with it and see how it works and how it moves, and observe what you would most naturally do to try to solve this integral. After playing with it for a bit, you'll probably reach the conclusion that your biggest problem right now is that radical 2020. What is it even doing there? So for now, we're just going to ignore it and focus on understanding the tangent function and reminding ourselves how the tangent function acts. To do this, we're going to look back at the unit circle and remind ourselves how we define the sine, cosine, and tangent using the unit circle. So in the unit circle, we define sine as the height of this arrow and cosine as the width of this arrow. And because we're in the unit circle, we can just call these y and x respectively. Notice that when we move the arrow 90 degrees counterclockwise, the y-coordinate remains positive, but the x-coordinate, the cosine, becomes negative. Now let's move this arrow back to where we had it a minute ago and add in the tangent function. The tangent function can be defined as just the fraction of y over x, which is really convenient for the way we have this set up. And also notice that at this 45-degree angle, it equals 1, which makes sense because y and x are the same, and anything over itself is 1. We can rotate the arrow to be flat against the positive x-axis, and notice that the tangent is now 0, because y is 0, and 0 over anything is 0. We can also rotate the arrow to be pointing straight up at pi over 2, and notice that it's undefined, or infinity. This is because as we're pointing very, very close to straight up, x becomes very, very close to 0, and any number over a very, very small number that's getting closer and closer to 0 is just going to blow up to infinity. Now, I should really stop here and point out that I'm not being as technical as I should be. A function can't evaluate to infinity. In order to have an answer like that, we need to involve limits. And even then, the limit of the tangent function as we approach pi over 2 doesn't exist, because from one side it equals positive infinity, and from the other side it equals negative. But for our purposes in this integral, all we care about is that it's getting bigger and bigger and bigger. It doesn't matter if it's positive infinity or negative infinity. And finally, let's just point out one other fact about the tangent function, that as we rotate it 90 degrees, we alternate between -1, +1, -1, and so on. What this means is that every 180 degrees, or every pi radians, the function is periodic. It repeats itself. Now armed with this knowledge of the tangent function, let's look back at our original function and try to plot some points out. So let's try plugging in 0. We know that tangent of 0 evaluates to 0, and 0 to the power radical 2020 is still 0, so we have 1 over 0 plus 1, or just 1. Next, let's plug in pi over 4. We saw that tangent of pi over 4 is 1, and 1 to the power 2020 is still just 1, so we have 1 over 1 plus 1, or just a half. And finally, let's plug in pi over 2 and remember that it approached infinity, or a very large number, and 1 over a very large number raised to any power is gonna approach 0. Now that we have some points and knowledge about what our function looks like, let's actually try to plot it. And we're hoping that maybe some clue will pop out in the graphing of this function that then gives us a hint as to how we can begin to find the area underneath it. So to start off, let's plot that when x is 0, y is 1. And we'll add in these other points here, all spaced at intervals of pi, since we also know that our function must be pi periodic, just like the tangent function. We also know that if we plug in something close to pi over 2, the y value should be really close to 0. And again, we'll place points all spaced at intervals of pi, since again, this function is pi periodic. Since the tangent function is positive between 0 and pi over 2, we also know that this function must exist here, which means that the function moves from those upper dots down to those lower dots. But the problem is we don't know how it moves. Does it go like this, or does it swoop down first? It's really hard to say, but we actually have one other really important piece of information, which is that when x is pi over 4, y is a half, which means that we at least know that our function must pass through these center points. I want to pause here and just point out why I'm leaving out these other regions right here. It's because in these regions, the tangent function returns a negative value, and we're putting that negative value to the power of radical 2020, which is an irrational number. And any negative value to an irrational number is going to return something complex, so we can't actually graph these numbers in the space that's defined here. Okay, so now that we've got a pretty good idea of what our function looks like, let's actually focus in on the region of this function that the integral is asking us to look at, this region from 0 to pi over 2. Let's shade in the area that the integral is asking us to find, and notice something really unique here, that if this curve is just right, we'll be able to flip the area in that top part of the graph over into that negative space, and call the entire area just the base times the height. But that kind of just begs the question, what do I mean by if this curve is just right? This is actually going to lead us to a discussion of odd functions, and what makes a function odd. So, even if you don't know the definition of an odd function, you've surely seen them before. They look like this, or maybe this, or maybe this. We can characterize them visually as passing through the origin and looking like you could kind of flip them over the origin and they'd be the same. But for our purposes, we're going to want to come up with a more technical definition of an odd function. So something we could imagine is sending out two dots from the origin in equal and opposite directions on the x-axis. And we could define an odd function as one so that when you do that, those red dots have to travel in equal and opposite directions in the y in order to reach the function. In comparing the coordinates of these dots, we'll always find that the numbers are exactly the same, but the signs for both the x and y are opposites. Notationally, we can represent this as saying that for some function where we imagine plugging in a positive x value and returning maybe a positive y value, if we were to plug in a negative x value, we should expect the negative version of that y value. Now let's remember the function that we're trying to integrate. What we meant by just right was that it's odd about that center point between 0 and pi over 2. But there's a problem if we want to use this test in the top left corner to figure out whether or not our function is odd, because the center of the function we're looking at right now is at the origin, and the center of our function is somewhere out here. So if we want to use this test we've come up with to see whether or not our function is odd, we're going to have to first shift it down by a half and then to the left by pi over 4. Algebraically, that's represented by subtracting a half from our function and then adding pi over 4 to the input of the function. So now that we've obtained this shifted version of our function, we want to test if it is in fact odd about the origin, and we do that by plugging in negative x instead of x. And our hope is that the result of doing this would be the same as just adding a negative sign to the outside. Since the only place x shows up is inside of the tangent function, we can boil this whole problem down to just understanding what happens when we flip that positive x to a negative x inside of that shifted tangent function. Now, you can just use the sum and difference formulas for the sine and cosine to figure out what happens when we do this, but it turns out there's a really nice visual way to understand what goes on when we flip the sign of that x value. To see this, we need to return to the unit circle, and this time I'm going to send out two arrows, one at positive theta and one at negative theta, representing our plus x and our minus x. And to each of these, I'm going to add pi over 4, creating a green arrow and a red arrow. The tangent of this green arrow is the same as the tangent of x plus pi over 4, and the tangent of this red arrow is the same as the tangent of negative x plus pi over 4. So let's name some of these values. We'll call the x-coordinate of the green arrow negative x, and the y-coordinate y. The tangent, accordingly, is y over negative x. But notice that for the red arrow, it looks like its height is the same as negative x, and its width is the same as y. Now, we don't know for certain that that's true right now, But let's just pretend for the moment that it is. The tangent of the red arrow would then become negative x over y, the exact reciprocal of the tangent of the green arrow. Let's move around our blue arrows, which determine the position of the red and green arrows, and play this game again. Here we'll call the x-coordinate of the green arrow x and the y-coordinate y, making the tangent just y over x. But again, notice that it looks like the base of the green arrow is the same as the height of the red arrow, and the height of the green arrow looks like the same as the base of the red arrow. If that's true, then the tangent of the red arrow again is just x over y, the reciprocal of the tangent of the green arrow. It turns out that wherever you move these blue arrows, so long as they're always at positive and negative versions of one another, the x and y coordinates of the red and green arrows will always be reciprocals of one another, and therefore the tangents will also always be reciprocals. This gives us a really nice identity for plugging in a negative input to this function. It's just the same as taking the reciprocal of that function. Now we're finally ready to test whether or not this shifted version of our integrand is actually odd. And I'm writing the radical 2020 as just an n right now, just so this whole process looks a little cleaner. It'll help us if we first take this function and make it all into one fraction. So I'll multiply a 2 on the top and bottom of the left-hand side, and I'll multiply the right-hand side by a tangent on the top and bottom. We can now combine the numerators into one fraction, and let's just hold on to this in the corner for now, while we work on plugging in negative x to that same fraction. The first thing we can do is turn all of these tan of negative x's into 1 over tan of positive x, as we just learned from our lesson with the unit circle. We can then multiply each of those 1's by tangent over tangent, which will allow us to combine the top and bottom each into their own fraction. Now, using the fact that dividing by a fraction is the same thing as multiplying by the reciprocal, we can just pull the denominator out over here on the right. And notice what happens once we flip the denominator. We get these cross terms that cancel out. The resulting fraction looks insanely like the fraction we started out with, and sure enough, once you rearrange the terms on the top and pull out a negative, you get the original expression just multiplied by -1. Alright, so it took a while to get here, so let's recap what that even means. It means that the function we started out with, once shifted to be centered about the origin, is an odd function, which means that once we shift it back to its original position and look at the area, we know that this curve does have the property that we can rotate the top of that area around. We can now finally find the area simply by multiplying the base times the height, or pi over 2 times 1/2. So the area is just pi over 4. Remarkably, this really is the solution to this integral. And I understand that maybe for some of you this feels like a somewhat unsatisfying solution to the problem. It wasn't necessarily super rigorous, we made a lot of assumptions, and we never even took into account that radical 2020. At the end of the day, this is just how I solved the integral. I'm sure there are lots of other ways, and I'd encourage you to go out and find them. I'll leave the more rigorous proof of this up to you, but here's how you could begin. You could start by realizing that since we never used that radical 2020, it probably doesn't matter what value it is. It's not going to change the value of the integral. You could then prove this statement by calling radical 2020 t and showing that the derivative of the integral with respect to t is 0. This statement effectively translates into saying that as you vary t, the area under the curve remains unchanged. And you'll also probably want to use Leibniz's rule for integration and turn that derivative into a partial inside the integral. The beauty of this proof, and part of what makes this integral so unique, is that once you prove that statement, t can be whatever you want it to be. You can choose it to be 2, which means that the denominator evaluates to just secant squared, which means the entire integrand just evaluates to cosine squared. So there you go. I hope you like this integral as much as I did. In my book, this definitely goes down as one of the most creative and unique integrals I've ever come across. And let me know what other solutions you guys come up with.